Okay, so here's where we were last time. We were talking about some physical examples. I like to call these metaphors. These are physical manifestations of what the divergence theorem is talking about. So this, again, my favorite one, I don't know, current favorite, I go up and down, is if you have a point light source, approximately a point, and so typically like a little LED is a very small little source of light. That creates a vector field representing the flow of photons. You can talk about the flux of that flow through the kind of the glass part of the light bulb. It's more plastic these days. And compare that to looking at what the divergence is on the inside. And what we found is that divergence points to literally where the light is coming from, right? So flux on this boundary says grand total how many photons are flowing out of the bulb. Divergence points to exactly where they literally came from, right? Which again is this point of view that I pushed in the past that flux doesn't happen on the boundary; it happens in the interior, and divergence tells you where. This is the perfect example of literally that. Right? Then we talked about this other example of a very different kind of a fluid, more typical, I guess, kind of a fluid, namely just air inside of a balloon. And the idea is if the air is expanding outward, then two things are happening. On the one hand, when air is expanding outward, you're going to have a flux of that fluid through the surface. The other thing is, if air is expanding outwards, then inside of your fixed ball, there's less air, right? Because it's expanded outward beyond your sphere. And so less air means less density. And here the divergence is pointing to, okay, to what extent in any given area, to what extent is the density decreasing, right? And of course, this being a gas like air, the air pressure, and therefore the air density, assuming constant temperature, has to be the same, right? And so that's why the divergence here is constant. So you get different interpretations of divergence because they're different kinds of fluids. Okay, so last comment I wanted to make, and this is really supplemental, so I'm going to be really quick about this. These two different types of fluid, the photon type of fluid is where the fluid is being generated. I mean, we're literally making photons when you have a light bulb. But the photon density isn't out there just changing with respect to time, right? How many photons there are in a given vicinity is always pretty much constant. On the other hand, this other kind of a fluid, namely the air, the density is what changes, but we're not creating air. It's just moving around, right? So I just want to point out that these two different features can be combined. And this equation here is a nice little summary of how to think about how to combine these, and I'm just going to very quickly talk about how to visualize this. So if you have a region here, some green here, lumpy region, and let's imagine that fluid is being created in the inside. So I'm just gonna draw a little dot here. This dot represents that fluid is just spontaneously appearing there. One possibility, one thing that created fluid can do is leave out of your region. In which case, it contributes to flux. On the other hand, here's another thing that fluid can do. If you have spontaneously generated fluid that just appears right there, another thing it can do is it can stay put, right? It can not leave your solid region. If it doesn't leave, you created fluid and it didn't leave, well then that's going to contribute to a rate of increase of the total amount of fluid. You create fluid, you got more fluid. Right? So the big idea then is that, so generation rate overall is there's only two things that can happen when you generate fluid. When you generate fluid, either it leaves or it doesn't leave. And so therefore, the total rate that you're generating fluid is going to equal to your flux plus the rate of change of your quantity. So this equation, you can think about this as I like to say, differentially per unit volume. Divergence results from taking flux differentially per unit volume. Mass differentially per unit volume gives you density, right? And then how to interpret that thing on the right side is intuitively a little bit weird. I call it generation rate density. I don't want that's a whole. We don't need to that's a distraction. We don't need to worry about that. My point is that whether you interpret divergence as telling you something about how density is changing, like our balloon example, or whether it's telling you where the fluid comes from, like in our photon example, just depends on how the specifics of your example and how this equation might be made to work. Given the specific. So the point is there are kinds of fluids that are sort of combinations of these two features. This is, again, cultural point. This is well beyond what we need to worry about in this class. Okay, let's talk about gravity. Gravitational fields y'all have seen before. We talked about these back in chapter 3, I guess it was. I think it was chapter 3 when we were talking about vector fields in the first place. This is an inverse square radial vector field. Inverse square, of course, because of the magnitude, being literally an inverse square magnitude. And radial because, of course, that is a radial direction right there. The vector factor there. Everybody on board? All right, so here is the very surprising fact, and that is that the structure of this vector field right here. When I say structure, what I mean is let's not get bogged down in the value of this constant, right? That structurally, it's the same no matter what the constant is. And by the way, also, structurally, it's the same whether this constant is positive or negative. For gravity, of course, it's negative, because gravity is an attractive force, not a repulsive force. Right? But independent of that constant, who cares? Structurally, looking at the fact that it's inverse square, the fact that it's radial, shocking fact. That's exactly what this vector field is. The vector field representing the flow of light out of a light bulb. Also, inverse square radial. Now, what are the odds that two very, very different physical things would be structurally the same? And okay, I don't know how to make that a probability problem, right? But I mean, it's an eyebrow raiser, and it's also an opportunity. And y'all may recall, and I've said the following a bunch of times in various contexts, but when some object behaves in a certain way, like if it behaves exactly like something that it isn't really, you can treat it as if it is that thing that it isn't, because it behaves exactly the same, and treating it like that other thing, you'll never go wrong. And that's what I'm going to do here. I've got this thing called gravity that's kind of hard to deal with. I mean, the gravitational field, what is it even? How do I think about that? It's hard to kind of get your hand on. But particles flowing out of a central source, it's pretty relatable, pretty easy. Right? So now I am not the first person to think of this idea. This is an old idea in physics. And so the metaphor that they go with, and I believe I understand it. I'm not an expert in physics, but I believe I understand this, might even possibly be considered to possibly maybe even be true. Not that it matters. We don't care. Right? It behaves like it's true. That's all we care about. But the model is to say that rather than thinking of this as how gravitational forces work, think of this as describing the flow of a bunch of little particles. And in the same way that light bulbs shoot out photons, we're going to pretend like every little particle of mass shoots out exactly the same way, little kind of photon-like particles, but they're going to call them gravitons to acknowledge the fact that these are describing gravity. So that's the theory, air quotes, theory that gravity is not this mysterious action at a distance. There's a planet way over there and I'm way over here, and magically somehow there's a force even though the planet is nowhere near me, right? What we can think of here is that, the planet's spewing out gravitons, and every time you get hit by a graviton, that is the universe telling you that, we're pulling you that way. That's the idea. All right, so gravitons communicating gravity as emitted particles emitted out of mass is the model that I want to use here. And it's a really, really valuable model as follows. I'm going to do a calculation here that would otherwise be ridiculously difficult, and I'm going to do it in just a couple of lines. Namely, it's this sort of this little square of equations here. We'll take these sides of this square one at a time. Start with this top line right here. This is arguably the easy one. Not much happening in this top line. It looks weird, but notice that's just a great big constant. We'll talk about why we put that constant in there in a second. But notice I've got this great big constant on both sides of the equation. That's perfectly legal. And other than this shared constant on both sides, this just says mass is a triple integral of density. That's easy. That's an old fact about mass and density. Everybody comfortable with that top line? All right. The left side, if you will, this equation right here, this is where I'm going to use the graviton metaphor. So remember, every little piece of mass, any given particle of mass, constantly shooting out gravitons, just like light bulbs are constantly shooting out photons. More particles shoot out more gravitons, just like more light bulbs will shoot out more photons. Okay? And then I ask the question, if I have a certain amount of mass on the inside here, now as I drew it here, the mass is only 1 point exactly in the middle, but for what I'm interested in that green equation, I don't even really care where the mass is. But however much mass I've got, wherever it might be, shooting out gravitons every which way, all of them flow out of my surface. Right? So whatever this surface is here, right? If you're interested in the flux through that surface, well, however much mass you have, be it there or there or there, each piece of mass is shooting out gravitons. They all count as flux because they all leave this surface. And so the amount of mass is directly proportional to the amount of flux. Everybody buy it? Now I'm going to point out that's just kind of a matter of just kind of thinking about the analogy and kind of, there's a couple of dots to be connected there and the way I'm approaching it. But if you were to take a purely algebraic approach to trying to make sense out of this, it's quite a bit more trouble. It's a lot more work. So this metaphor, this graviton metaphor, extremely helpful. Again, independent of whether it's physically true, don't care. Gravitational fields behave exactly like hypothetical graviton flow fields, so we might as well pretend that it's true. Okay, so that's that. And then lastly, we're basically there now, as it turns out. Here's just the Gauss's divergence theorem, that flux is a triple integral of flux density. Now, it's just a matter of writing it down. And then we look at this equation. Now I have concluded, by way of this kind of three-step process, that these two triple integrals are always the same for any solid. And if you have two expressions that are integrals over the same surface that are always equal, that means the integrands have to be equal. And so what we have accomplished here, just again, by a clever metaphor and connecting a couple of dots, we have been able to compute the divergence of whatever gravitational field, no matter how many points of mass you have. Even if your mass, instead of being just as a point, even if it was kind of distributed irregularly throughout your surface or throughout your solid, even if it was, something like this, where there's just bazillions of little particles, each putting out its own gravitational field. Oh my God! Writing down the gravitational field here would be horrifyingly difficult. This gravitational field created by that mass, horrifyingly difficult. And then I have to compute the divergence of it on top of that. Very difficult problem. Our clever little three-step argument instantly shows us, it's this constant times mass density. I think it's a really cool argument. Okay, now real quick, there's a linguistic opportunity here, so I'm going to take it. Mass causes flux. One way to say this, again, think about the graviton metaphor. More mass, more gravitons, more flux. So mass creates flux. And then if you come over here to the other side, you could interpret this as saying that mass density creates flux density. Keep in mind, that's one of our interpretations of divergence. Divergence is flux density. So mass creates flux, mass density creates flux density, and the thing that connects them, right, the way that I connect these two clearly, closely related ideas is Gauss's divergence theorem. So this is one of the extremely powerful things about Gauss's divergence theorem. It allows you to connect ideas, global ideas, and local ideas in this powerful way. All right. Okay, so you say you have no intentions of ever becoming an astronaut. Gravitational field will always be straight down, constant magnitude for every experience you're ever going to have in your entire life. Who needs to understand gravitational fields? They're effectively constant as far as we care, right? I have the strong intention myself of never leaving the surface of the Earth. Right? Even if what's his name, the billionaire guy, if he invites me, we want you on the next space shuttle. Forget about it. Right? Not going. Pass. So why do I need to understand gravitational fields? And I have a good answer for that. It's because you're going to need to understand electric fields. Electric fields are not constant and boring near the surface of the Earth. There's unbelievably complicated electric fields in my phone right now, right? And if you're going to be an engineer, you're going to be doing stuff with electronics in any sense, you're going to really, really need to understand electric fields. And there's a lot to it that's complicated. The fundamentals of how they behave are extremely important. So, how are we going to understand electric fields? What does this have to do with gravity? Well, electric fields are also inverse square radial. They're just like gravitational fields. Different constants, different units, sure. But structurally, they are exactly like gravitational fields. So I will reveal that when I made it through my physics major way back when, every time I had to think about an electric charge and the resulting electric field, in my mind, I was like, okay, charge, you know what, that plays a role kind of like mass. And the resulting electric field, it's kind of like the resulting gravitational field. And likewise, you can equivalently, instead of thinking of mass as shooting out little particles called gravitons, you can think of charged particles as shooting out little particles that because they communicate electric forces, you're going to want to call them electrons. You can't. They're not electrons. That word's been used for something else. Tragically, we have to kind of think more creatively in terminology. They're photons. Anyway, a different kind of photons. So the point that what they're called doesn't matter. Charge can be thought of as emitting little particles that communicate electric fields. And so all of the analogous arguments go through. It's perfect analogy. And so if you want to understand electric fields, understanding gravitational fields is a pretty good first step. Now, what's the advantage? Like, why would you translate one problem into a in fact morally equivalent problem? And this is just about experience. I have experience with mass. I encounter mass every day. I am made out of mass, right? I experience gravitational fields every day. This is all very relatable, and the objects being discussed here, I can almost feel them. I can literally feel some of them, right? So I find this very relatable. Whereas electric fields, electric charges, not particularly relatable. I mean, it wasn't that long ago that no human was aware of their existence, right? So not that relatable, kind of weird and creepy. So I think it's really valuable that anytime you want to think about electric charges and electric fields, you can just by analogy think about mass and gravitational fields. So anyway, that's why I like this analogy. How are we doing? Is everybody with me? Okay. All right, so next big theorem, Stokes's theorem. Y'all are going to notice patterns. I went to a lot of trouble when I was writing these notes to make sure that everything lays out on the page in a highly analogous way for each of these various boundary theorems that we've talked about. So Green's theorem, the two-dimensional divergence theorem, Gauss's theorem pretty recently, right? And now moving on to Stokes's theorem. And so the patterns are going to be overwhelming. There are different details appropriate to the different geometry. The big picture ideas are all the same. So first we need to talk about orientations of boundaries. If you have a surface, to be more clear, if you have an oriented surface, so a surface with an understood orientation, namely there is a well-defined which direction is positive direction through that surface. Again, an arbitrary choice. Let's talk about the boundary. The boundary is going to be, of course, this kind of curve like this. There's that boundary. It's the edge, right? Edge of the surface. Well, if you have an oriented surface, you would expect that the boundary should also have an orientation. And there's two different directions this curve could go. It could be that could be positive direction along the curve. It could be that that's the positive direction. And we have to make a choice. So again, this is a matter of convention. It is arbitrary. It didn't matter 150 years ago, but a choice was made. A convention was accepted. We've got 150-ish years of standard accepted policy on this, and so we have to go with the standard. So here is the rule. It is a little bit of a weirder rule. Gauss's, looking at three-dimensional solids, the rule was very simple: away from the solid, very crisp, right? When we're talking about areas in 2 dimensions, always walk around so that the region's on your left. That's pretty straightforward. This one's weirder and harder to describe. Here it is. You start with your right hand. Thumb in the direction of the orientation of the surface, whose boundary you're talking about. Your fingers want to curl a certain direction. I remind you, right hand only. Whichever direction your fingers are pointing, if you will, around your thumb, that defines what I'm going to call a swirl, and I'm going to get rid of the thing there. That defines what I'm going to define a swirl. In this case, it's kind of that way. So again, right hand in the direction of the normal, fingers swirl. That swirl will sideswipe up against the boundary in the direction that defines the standard orientation for that boundary curve. What do you think? Everybody follow the rule? It's arbitrary. Why the right hand? Why not the left hand? Yeah, well, I don't know. Talk to Stokes. Is everybody happy? All right, so we have a notion of boundary orientation. Let's see here. We're going to have to talk about accumulation. Nobody's stunned there. We keep talking about accumulating quantities all the time. That's how all these theorems work. I claim that, kind of like with Green's theorem, boundary circulation is going to be our accumulating quantity in this theorem. So I claim that boundary circulation accumulates. And to be more specific, boundary circulation accumulates over surfaces. So what I mean is, specifically, it is surfaces, like what I have drawn here, that if you look at the boundary circulation on the whole surface, or if you kind of chop it somewhere in the middle and then look at the boundary circulation on the left and the boundary circulation on the right, the whole is the sum of the parts. Right? So specifically, it is the surface that you chop up into little pieces. Why does it work? That's, again, with kind of drawing it out and looking at the direction that the arrows point. I mean, ultimately, when you slice your surface, thus creating thus creating kind of a new edge there. Well, this edge is part of the boundary of S1 oriented that way. And again, you got to think about the orientation of S1. S1 is oriented like that, finger, swirl, etc., side swipes. It's going to be going that way. Right? And then now S2 is oriented in a consistent way, right? If S1 being oriented that way, that there has to be a continuous, you can't just cheat and decide right in the middle you're going to cut it and make it go the other way. No fair. Right? So S2 also oriented like so, thumb, fingers, swirl, etc. That's going to be oriented this way. And again, the new edge appears twice with opposite orientations as the part of S1 versus as part of the boundary of S2, and it cancels. Just like every other one of these boundary cancellations that we've seen in the past. So, boundary circulation, accumulating quantity. How are we doing? Okay. By the way, while I'm here, I'm going to point out, I think it's a healthy exercise to look at what I've drawn here as pertains to surfaces in space. And then look back in the notes to when we were doing the same thing as we were developing Green's theorem. That was a two-dimensional, can't really call it a surface because it doesn't live in space, but it was still two-dimensional just like this surface. It was just that it's two-dimensional inside of R2 instead of R3. But we drew practically the exact same picture. The cancellation it's oh my gosh, practically the same picture of why the cancellation happens. So it's very reasonable to say that all we're doing here is kind of developing kind of a three-dimensional analog of Green's theorem. And that's a very reasonable way to think of, we're in the process of developing something called Stokes' curl theorem. It's a three-dimensional version of Green's theorem. Okay, moving along. Any accumulating quantity can be thought of as having location within the region as follows. So if you have a whole surface here, let's suppose we're interested in mass, certain total amount of mass on this surface, and if I were to ask the question, how much of that accumulating quantity called mass is there on this little sub-region that I have here in green? look at just literally compute how much mass there is on that region. Just pretend like the solid isn't there. Whatever the computation for this little green region, that's how much of the yellow mass is in that green region. Right? Of course it is. The whole is the sum of the parts. I mean, this part tells you how much of the whole is in this region. And the same is true for any accumulating quantity, and in particular, it's true for boundary circulation. So the boundary circulation of the whole, being as it is the sum of the boundary circulations of the parts, if you want to know how much of the yellow boundary circulation comes from the green region, same deal. Just forget about the yellow, look at the green by itself, compute the boundary circulation. That's your answer. Right? So you can think of it as even though we, our sort of computations tend to go like this. I mean, this is how I compute a boundary circulation. It looks like it's happening on the edge. Again, illusion. It accumulates over the surface. The fact that I computed on the edge is I suppose, a convenience or something, but it's not really representative of certainly how you should be thinking about it. Okay. All right. So, therefore, this is an accumulating quantity that has a location. It behaves like a stuff, kind of like mass. And so we can talk about the corresponding density, how much of that accumulating quantity called circulation, which again happens in the interior. How much of that is there per unit size, in this case area? Namely, how big is that little piece of surface? Circulation per unit area, pretty natural thing to call circulation density. And again, it's just like mass density. Mass density says how much of the accumulating quantity called mass is there per unit size. Here, different accumulating quantity, circulation. How much of that is there per unit size? Circulation density. Everybody all right? Again, kind of like we did with flux density. Likewise, circulation density when we were doing Green's theorem, right? It was two-dimensional instead of three-dimensional, but same concept. Okay, so here's where I sweep some stuff under the rug. Technical calculations, they're mathematically important, but in a time-constrained situation in terms of what are you going to retain 5 years from now, 10 years from now, right? The details of that calculation, it would not bother me if you don't remember, and that's why I'm not going to cover it. But I do think it's really important just to have a working understanding and intuition for how Stokes' curl theorem works. It's very important to understand that circulation density relates to this being an accumulating quantity, and of course it's also very important to know the result. And here's the result. So I'm just going to write this down, claim that this is the answer. It's curl dot the orientation unit normal little n. Don't look for intuition on where that comes from. That's a bunch of calculations. Everybody all right? Yeah.
Back when we were talking about circulation density in 2D,
yeah,
you were saying if you dropped something in, how it would rotate. So
yeah.
Is there an analog of that in 3D?
Yeah, absolutely, and that's going to be about the last 10 minutes of the lecture. Yeah. Well, depending on how far I get looking at the clock, it'll either be the last part of today's lecture or the first part of Monday's lecture. Yeah. Totally. Yeah, no, absolutely. And good intuition. Yeah. Okay. Before I get to putting everything together, I do want to point out something that's a little bit of an eyebrow raiser. Let's talk about flux density for a second. You give me a vector field PQR. Flux density is divergence. It's x partial of P plus the y partial of Q, et cetera, et cetera. It only depends on the vector field. You can compute it straight from the vector field. In Green's theorem, circulation density, dq dx minus dp dy, it's only a function of the vector field. but look at this creepy weirdness. This circulation density depends on the vector field, and it depends on the orientation of the surface. We did not see this with Gauss's divergence theorem. We did not see this with Green's theorem. Likewise, you don't see this with the fundamental theorem of calculus. The densities are just functions of the quantities in question. End of story. The orientation doesn't matter. Here it does. A little weird, a little upsetting, a little disconcerting, a little worried that things are going to work out too differently here. But it turns out that this is actually going to be just fine. I just wanted to, this is a little bit of foreshadowing. But anyway, it turns out there's not a problem at all. Here's the final version of the theorem. I'll remind you, we started with this idea that we're going to think of circulation as being a quantity of interest. We make the observation that it's an accumulating quantity. Whole's the sum of the parts. Look at what this blue equation says. It's exactly, literally saying the whole circulation is the sum of all the little pieces of circulation. Right? So, whole is the sum of the parts. And then we make our usual density argument. That piece of circulation relates to the size by way of the density. And here's the density that I cited on the previous page. Curl dot in. So there you go. Notice the pieces fit together. The Legos fit together exactly the same way as our previous theorems. Here is what I'm going to call the first cut then on Stokes's curl theorem. But we are going to change the way we write this just a little bit. You'll notice, I'm sure, that in ds, right there, we've already got a name for that. It's a very convenient shorthand just to rewrite that as the ds vector. And having done that, now I can restate the theorem as this, which then says that a circulation can be computed as a flux of the curl of the original vector. All right, everybody good? Okay. All right, so this is Stokes's curl theorem. Now I'm going to show you an example, just a kind of a hands dirty example. Well, let's see here. Why don't I do that? There we go. So yeah, the question says let's compute this line integral. Notice that the vector field is given and the curve is given. And so you could plug and chug this. Keep in mind, when you're asked a question, it very routinely will not tell you what method you should use to answer the question, right? Certainly the real world doesn't, right? So very often, accordingly, questions on exams will not tell you compute this line integral using the following method. Sometimes I will if I have a specific interest. But this one doesn't, and so we have to decide. Now, I could pull back through the parameterization, and a lot of cases, this being one of them, that would just be a nightmare, right? Because keep in mind that is x, which means there's trig in my vector field, and this is y, which means there's trig. Even worse, there's trig inside of an exponential in my vector field. I don't like it. Right? I'm not saying it couldn't possibly work out with some algebraic good luck, but I'm just saying I don't like it, and I don't really want to go down that road if I don't have to. Okay. Next option. Again, thinking about how to compute this line integral. Well, let's see here. It's a line integral. I got an idea. Let's use the fundamental theorem of line integrals. It's right there in the name, line integral, right? So I'd be optimistic that we might be able to use the fundamental theorem of line integrals. Bad news, you can't. If you're going to use the fundamental theorem of line integrals, you need your integrand to be a gradient. Said differently, your integrand, you need to be able to find an anti-gradient. And as it turns out, and y'all can check me on this if you like, this vector field does not have an anti-gradient. Look all you want. You won't find it. It isn't there. So that was a crash and burn. So we're kind of out of ideas at this point. Is there any fortunate geometry? Well, not for a direct calculation of this line integral anyway. So what we're going to do instead then is we're going to compute this line integral, hopefully, by using Stokes' curl theorem. That's our last chance, and this is going to work out very nicely. Now, before we do, reminder, Stokes' curl theorem, here it is. As with all of our accumulation theorems, there's a catch. There's a yeah, but. And it only works when a certain not to be assumed condition is satisfied. And in this case, that condition is the fact that this has to be a boundary. Very importantly. Stokes' theorem only addresses the question of vector line integrals over boundaries. Right? That's why it's nice to use the term circulation, because circulation that's implicit in the word circulation. Right? So if your line integral is not around a boundary, forget about it. The Stokes' curl theorem doesn't apply. And I want to emphasize, this is not a minor point. This is not a, technically, or something like that. Look at the argument that we've made here, right? The entire theorem is based on this argument about accumulation, and the accumulation only works because we're talking about boundaries and the conventions that we've made on how to orient boundaries. Right, so this is fundamental to what the theorem is and how it could conceivably be used, that it only works for boundaries. And so we have to look at, question. Yeah.
Are there instances where you have a curve that's not a boundary and you try to force it into a boundary somehow by completing it?
By there's some clever situations like that, yeah. I have what I feel like are more convenient tools for dealing with that scenario, and I'm going to talk about that. It's another thing we'll talk about on Monday. There's a technique I like called surface independence. Very, very similar point, but yes. So yes, but not going to be particularly useful for us. Yeah, right. So let's see here. We have to make sure, if we're going to cite Stokes' theorem, we better make sure that our curve is a boundary. Reminder, our curve here, all we know about our curve is a parameterization, but I'm going to remind y'all the curve is pretty clearly in the xy plane. Cosine and sine makes me think circle. This minus sign makes me think reflection. If you kind of take those ideas, put them all together, it's not hard to persuade yourself that, in fact, what we have here is this unit circle oriented, as I've got it drawn there, oriented kind of what you might call clockwise as seen from above. Quick reminder, if you're in 3 dimensions and you want to talk about clockwise, counterclockwise, don't forget perspective matters, right? This looks clockwise to me. It looks counterclockwise to y'all. Right? So if you're going to say clockwise or counterclockwise in 3 space, you have to say as seen from where. Okay. So is this a boundary? A lot of students get this wrong. A lot of students think, no, it's isn't it always supposed to be counterclockwise or whatever, right? First of all, no, that's not the rule. The rule about orientations and boundaries is what we have here. It's this business about thumbs and swirls of your right hand, right? Thumbs and swirls. And so what we have to ask ourselves here is, looking at this picture, let me clean up so I can get the mess out of the way, and then I will do this. Is this curve a boundary? And in fact it is. Check it out. If I were to take the orientation as being downward, like so. That being the orientation on this surface S, like this. Now, if I ask what's the boundary of this surface S, well, thumb in the direction of the given normal vector, looking at my fingers, thinking about the swirl that creates a swirl that goes that way, which sideswipes that way, which is the correct direction. So sure enough, this curve, perfectly fine. Our given curve is a boundary of the downward oriented yellow unit disk there that I've got drawn. Is everybody on board with that? Yeah. Oh, I'm sorry. Is everybody happy? Okay. By the way, if you're not sure which way it goes, you just have to kind of trial and error. I mean, you can just say, all right, well, I don't know how this is going to work, but I don't know. How about let's try if we were to orient it upward, right? Does this work? And then, thumb and fingers and swirl, and you'll find yourself swirling this way, which has you going this way on the boundary, which is wrong. So sometimes you have to kind of trial and error. Up, failed. Then you try down, and down works. Okay, so it's kind of all over, but the shouting, if this thing will cooperate here. Okay, there we go. So we have a boundary. Our curve is a boundary. The question then that we're supposed to compute a vector line integral over C. Well, that is a boundary line integral, aka a circulation. Stokes' theorem tells us that we can compute that with a flux of the curl, like so. And how you compute that flux is up to you. And again, you have options, and you could parameterize the surface, which wouldn't be bad. It'd be a reasonable thing to do. But I like to point out that there are often little bits of good fortune. And in this particular case, keep in mind, our normal vector is easy to write down. Our unit normal is a freebie. You see it right from the picture. The curl, as it turns out in this case, now make sure that you know how to do the algebra on this. Make sure you can compute the curl of a vector field. And weird though that vector field is, curl's easy, as it turns out. And so our integral turns out to have a very convenient integrand. The integrand's just -2, and of course, being a constant, that just factors out. And now you have -2 times the area, and you win. Everybody happy? All right, so always be on the lookout, always head on a swivel looking for little free opportunities like this that do present themselves surprisingly often, yeah.
So is like just seeing the orientation the only way to find n, or is there another?
So, well, I mean, so the other thing you can do is you can parameterize, and then you can compute the capital N by the usual formula, but then you still do have to think about orientations, because anytime you parameterize, you're basically parameterizing randomly. And it's a coin flip as to whether you parameterize the wrong way or the right way. So you just have to make sure that you parameterize downward. And if you inadvertently parameterize upward, which the graph parameterization would give you in this case, then you got to throw in that extra minus sign. But yeah, you could do that. I'm just trying to encourage you to look for opportunities to avoid that extra effort. It's very good. All right. And let's see here. We have 30 seconds that I'm sure I owe you. So we'll call it a day right there. We'll pick up here on Monday. Y'all have a great weekend. See you later.